Rowland from Algebra University will be telling us about Sinkhorn limits and the combinatorial structure.
Thank you, Joel, and thanks to everybody for being here. So this is joint work with Jason Wu, who was a high school student when we did most of this work and is now an undergraduate at Cornell. And this talk is going to start off sounding like a linear algebra talk. Then it's going to turn into a number theory talk. And at the end, we will get to some combinatorics. So the combinatorics that arose here arose in we didn't go into this project expecting any combinatorics to show up. So it was pretty neat that we found some. So the question is, you start with a square matrix with positive entries, and the goal is to turn it into a matrix that's close to the original matrix in some sense. That will leave vague for now, but that is doubly stochastic. In other words, is an element of the Birkhoff polytope. So the row sums are 1 and the column sums are 1. So for example, here's a 2x2 matrix, 4, 1, 2, 1. And just completely naively, if you're trying to get a doubly stochastic matrix out of this matrix, a naive thing to do is to scale the rows first. Right, so initially the row sums, the first row sums to 5, the second row sums to 3. Those are not equal to 1, so we scale the rows, divide the first row by 5, and the second elements in the second row by 3. And so at least we have a row stochastic matrix now. The columns do not sum up to 1, but we can scale the columns to get them to get the column sums to be 1. And then great, right? No, because by scaling the columns, we broke the row sums, right? So now we have a column stochastic matrix that's not row stochastic. But no problem, we can scale the rows again. So to scale the rows again, now the row sums are 1. We've broken the column sums, so now scale the columns so that they're 1. And if you keep doing this, alternating between scaling the rows and scaling the columns, it turns out that you get that the limit exists of this process. So this process converges to something. This is called the Sinkhorn limit of the original matrix we started with. And the limit exists. This was proven in the 60s by Richard Sinkhorn. And so we call it the Sinkhorn limit after him. And for this particular matrix, if you stare at these numbers for a while, you can probably guess what they are. Anybody see any evidence for what these numbers might be exactly? Huh?
Are they integers of the sum?
So this 0.414 might remind you of the square root of 2. And so once you see that, it's pretty easy to figure out what these entries are exactly. So they do indeed involve the square root of 2. So Sinkhorn limits really should be better known than they are. I only heard about them right before we started this project. They have a huge number of applications in computer science and in other areas. In computer science, they're used to, if you're solving a linear system of equations numerically, you can use them to precondition the system of equations to improve the stability, the numerical stability of your solution. They're useful for approximating a matrix, which has applications in determining whether a graph has a perfect matching. And this iterative scaling process was also rediscovered many times independently in other areas, in predicting telephone traffic, in transportation science, economics, image processing, operations research, and most recently in machine learning. Most of these I have not looked into, but this predicting telephone traffic paper, I did read carefully enough to understand what was going on. So this is a paper by Krauthoff in 1937. This seems to be the first time that anyone looked at this iterative scaling process. It's in Dutch, but there's an English translation available if you don't happen to read Dutch. And I made a YouTube video about this a few months ago, so you can check that out if you're interested. The basic idea is that if you're a telephone company in the 1930s, when telephones are being rapidly adopted, you want to know how many how many telephone lines you're going to need next year based on the telephone traffic this year, right? So a certain number of more people are going to put telephones into their houses How does that gonna, you know in each city, you can predict in each city how the telephone population is gonna grow, but you want to know in the network between cities, do you have enough telephone lines or not? And there's an amazing 100-page survey article about Sinkhorn limits and generalizations and abstractions. It's on the archive. It's from 2016. So I refer you to that paper for a lot of other applications and generalizations. But for all these applications, you only need to run the iterative scaling algorithm a finite number of times because you're just interested in an approximation to the Sinkhorn limit. So a relatively new question is, what are the exact values that you get when you iteratively scale a matrix? What are the exact entries of a Sinkhorn limit? So for example, we saw this matrix, 4, 1, 2, 1. This is going to be our notation for the Sinkhorn limit of a matrix. We saw that it's this matrix. In 2019, Mel Nathanson found a formula for the Sinkhorn limit of a 2x2 matrix with positive entries. So this is his formula. He posted the paper in 2019 and it was published in 2020. So for a 2x2 matrix, ABCD with positive entries, this is the Sinkhorn limit. It's the square root of AD, square root of BC, square root of BC, square root of AD, and then you divide by this sum. And you can check that for this matrix, you do get this back. So for example, we have square root of AD, that's going to be a 2. And square root of BC, that's going to be that's where the square root of 2 is coming from. So you get some square root of 2s, and then you can simplify it, and you'll get this. For a symmetric 3x3 matrix, that same year, 2019, Zeilberger and his computer, Echad, determined the entries of the Sinkhorn limit. So this is a symmetric 3x3 matrix. This is just for the top left entry. They did it for the other entries as well. But this was computed using Grosvenor bases, which I'll talk more about in a minute. The top left entry of the Sinkhorn limit of a symmetric 3x3 matrix satisfies a quartic equation. And here are the coefficients in all of their gory detail. So these coefficients are all polynomials in the entries of the matrix A. But I think the takeaway here is that the entries are algebraic, which is maybe surprising, right? Because we're getting this from a limiting process, but nonetheless, you get algebraic entries in this case, and the degree is at most 4. And before we started working on this project, this was it. So it was known for 2x2 matrices and symmetric 3x3 matrices. So even for general 3x3 matrices, it wasn't known what the entries of the Sinkhorn limit are. So here's an example of a 3x3 matrix that's not symmetric. Here are the entries of the Sinkhorn limit, approximately. Can we identify these 9 numbers? So one way to do this is to first compute, let's say, the top left entry to high precision. How do you do this? You can start, instead of starting with these integers and just basically you want to treat these integers as high precision real numbers. So treat this as 2.000, 100 zeros after the decimal point, and then start scaling the rows and columns. You'll lose a little bit of precision, but you can still compute arbitrarily. If you take more precision in the input, you'll get more precision in the output when you scale. And then you just scale until you get a fixed point up to 50 digits or however many digits you want. So you can compute one of these entries to very high precision. Since the other examples we saw all gave algebraic numbers, we can assume or at least guess that the result is going to be algebraic here as well. What is a good guess for the degree? Well, since for the symmetric 3x3 matrices, they had degree 4, the entries, so we might guess that this number is also a degree 4 algebraic number. And then to actually identify it, you can use what's called the PSLQ algorithm. So this is an algorithm that looks for an integer linear relation among a finite set of real numbers. So here your real numbers are going to be, this is your approximation to x. You're going to raise that to the 4th power, the 3rd power, the 2nd power, take x itself, and also take 1. You look for an integer linear relation among those 5 numbers, and that's going to be close to, PSLQ will give you some coefficients B4 through B0 to make that linear combination fairly close to 0. So this is what you get for degree 4. And then the question is, is this actually right? Is this the real description of this number, or is this garbage? And you can check that by computing x to even more precision and running PSLQ again on that even higher precision approximation to x. And when you do that, you don't get the same polynomial. So this polynomial is actually garbage. So, there are two possibilities. Either you're not looking at an algebraic number after all, or maybe we need to bump up the degree. So let's bump up the degree to degree 5, run PSLQ again, now looking for 6 coefficients of this quintic equation. You get this polynomial. This is also garbage. You don't get the same polynomial when you increase the precision in x. So maybe we bump up to degree 6 and we start getting a little sweaty. You get this polynomial, but this polynomial does stabilize when you use more digits for your approximation to x. So this seems to be really the minimal polynomial satisfied by the top left entry of this Sinkhorn limit. And in the summer of 2019, I had 2 high school students working with me so Hofstra has a summer science research program for high school students. And this is what they did that summer. They took matrices with positive integer entries, ran the iterative scaling process till they got a fixed point, and then used PSLQ to try to guess the polynomials that were the representations of the entries, and look for patterns in the polynomials, and in particular try to understand what the degree was doing as you increase the matrix size. And so their conjecture was that for 3x3 matrices, in general, the degree isn't 4 like it was for symmetric 3x3 matrices. The degree is actually 6. So all the entries, conjecturally, all the entries of the Sinkhorn limit of a 3x3 matrix are algebraic numbers with degree at most 6. Yeah, so PSLQ, it's such a great algorithm and it's such a crummy name. The PS, I'll tell you what these stand for, but it's going to be disappointing. PS stands for partial sums, and LQ stands for LQ decomposition. And these are just tools that were embedded in the algorithm, and so it doesn't tell you. You'd have to really read the algorithm to understand why it's called this. So yeah, so we should really try to rename this algorithm. Maybe we should just call it the great integer relation algorithm or something like that. So I want to just mention here, why are we just focusing on the top left entry? So it turns out that if you have a formula for the top left entry as a function of all the entries of A, then you actually can get formulas for all the entries as functions of A. And that's because the iterative scaling process doesn't care about the row order or the column order, right? When you're scaling the rows and scaling columns, it doesn't matter what order you have the rows in. If you permute the rows and scale, that's the same thing as scaling first and then permuting the rows. So really, we just need a formula for the top left entry of the Sinkhorn limit, because once we have that, you just permute the entries of A in your formula. You get formulas for all the other entries of the Sinkhorn limit. So for a 3x3 matrix, can we determine the top left entry of the Sinkhorn limit? And you can write out a system of equations for doing this, right? So every time you scale the rows, that's equivalent to multiplying on the left by some diagonal matrix. And every time you scale the columns, that's equivalent to multiplying on the right by some diagonal matrix. And so by scaling the rows and columns, you're multiplying on the left, multiplying on the right, multiplying on the left, multiplying on the right. But you can sort of, so you're going to get an infinite product on each side. But it turns out that these infinite products converge. And so you can get from A to its Sinkhorn limit by multiplying a single diagonal matrix on the left and a single diagonal matrix on the right. So we can just set up, we don't know what these are, but we can set them up as variables and see if we can solve for them. So this is a matrix equation for relating A to its Sinkhorn limit. if you unpack this and see what it says about each of the 9 entries, you get 9 equations. So for example, the top left entry is just R1 times the top left entry of the matrix A times C1. And then we also have constraints that our matrix is doubly stochastic, right? So we have 6 equations for the row sums and 3 equations for the row sums and 3 equations for the column sums. And what we want is, from this system of equations, we want S11, the top left entry of the Sinkhorn limit, just in terms of the original matrix, just in terms of these 9 entries. Yeah, so this says, so we want S11 in terms of the A's. We have a system of 15 equations, and it turns out that we have 14 variables that we don't care about. The 3 variables here, the 3 variables here, and then the 8 variables in S in the Sinkhorn limit that aren't the top left entry. And if this were a linear system, of course, we could do this with Gaussian elimination. But it's not a linear system because you have products in these equations. Fortunately, there's a generalization of Gaussian elimination that, in theory, will let you solve systems like this. So what you do is you can compute what's called a Grosvenor basis. The problem with computing a Grosvenor basis is that once your systems get sufficiently large, it's not like Gaussian elimination, which scales pretty well with the size of the system. The worst case running time for a Grosvenor basis computation is really bad. And so, for any given example, if you're not an expert in Grosvenor basis, which I'm not, you don't have a sense initially of like, okay, is this going to be feasible to actually compute the solution or not? This one, we were able to get it to work with some tweaking. So we were using Mathematica. Mathematica has built-in functions for computing Grosvenor bases. The default settings didn't work. It ran for several hours and it didn't finish. But when we modified the algorithm and changed the settings, we were able to get it to run in, I think, just like less than a minute or something like that. And sure enough, you get a degree 6 equation. So this confirms the conjecture of my 2 high school students from 2019. So S11 is, I'm going to write that as X. So S, the top left entry of the Sinkhorn limit, satisfies this equation. And the coefficients are pretty bad, but we have them explicitly. Here's B6 and B5. Here's B4 and B3. And here are the last 3. So this is an answer. It's not that intuitive, maybe. Hopefully, ideally, there would be a better formulation that we can extract some intuition from, or at least extract some predictive value. Like, does this tell us anything about what the equation should look like for 4x4 matrices? And amazingly, there is a better formulation. And the big hint is that B6 is actually pretty nice when you write it in factored form. So B6 is a product of 5 terms, 5 factors. And if you stare at these for a minute or two, you'll notice that each one of these is a determinant. So this last factor is the determinant of the full matrix A. And these other factors are determinants of 2x2 matrices that we get from extracting 2 rows and 2 columns from A. So these are called minors. This just means a determinant of a matrix you obtain by extracting rows and columns. So B6 is a product of 5 minors. And not just any 5 minors. These 5 minors all involve the top left entry, A11, which is, a good sign because we're looking for the top left entry of the Sinkhorn limit. So there's some compatibility that's being hinted at here. So it's the product of 5 minors that involve A11. I'm going to also add this, and it's also in this product there are 0 factors that do not involve A11 or more generally the top row, the first row and the first column. This is going to play a role in a second. So B0 also has a nice factorization. B0, this is a determinant. This is a 2x2 determinant. And Jason pointed out, and I was skeptical that this was going to be useful, but it turned out to be really useful, that these terms are also determinants. They're just determinants of 1x1 matrices, right? So don't ignore determinants of 1x1 matrices. So this is B0 is the product of zero minors that involve A11 and 5 minors that do not involve A11. And then there's this A11 to the 5th term. You can kind of explain that away because there's an A11 to the some power term in each of these coefficients. So you can, maybe this is just a homogeneity factor that's coming into play. So let's not worry about that too much. Yes, yeah. So these all have all they're homogeneous polynomials of degree 11. Yeah. So what we really want to do is, we have nice descriptions for B6 and B0. Can we sort of use this to get nice descriptions for the other coefficients? And so ideally, we'd like to be able to interpolate somehow between products of 0 minors involving A11 and 5 that don't, and products of 5 minors involving A11 and 0 that don't. The problem is, if we're going to go from B0 to B6, we don't have enough room here, right? This really should be 0 to 6. But we can easily fix that by multiplying, just scaling this entire equation by A11. And then A11B6 is the product of 6 minors involving A11 because A11 is a minor that involves A11. And now, in fact, it's all of the minors that involve A11. So that's nice. We sort of maxed it out. And A11B0 is the product of 0 minors that involve A11 and 6 that don't. What's the new minor that we introduced in B0? It's the factor 1, which is the determinant of the 0 by 0 matrix. So also don't ignore determinants of 0 by 0 matrices. And then we have A11 to the 6th running around. So the guess is that the intermediate coefficients somehow involve products of k minors that involve A11 and 6 minus k that don't. And so now there's not just one of these products. For B0 and B6, there was just one product, but now there are multiple. There are many of these products. So what do? Maybe we take a linear combination of them. So that was the guess, and amazingly, this turned out to work. So there's some notation here that's not fully defined. I'm going to define it on the next slide. But this is the compressed version of that degree 6 polynomial, having introduced some notation that we haven't defined yet. So for a general 3 by 3 matrix with positive entries, the top left entry of the Sinkhorn limit satisfies this degree 6 equation where these are the coefficients. So the first thing I want to point out is that BK involves the sigma thing where I have K. Basically, I have a matrix here, but don't think of this as a matrix. Each of these pairs RC is a set of row specifications and column specifications. And in the BK coefficient, each of these has K row and column specifications. So each of these specifies a minor. So you can think of this as extracting 0 rows and 0 columns. This is extracting 2 rows and the second row and second column rows 2 and 3, columns 2 and 3. But then for B2, we take 2 minors and put them together in different ways. So each of these sigma of S's, so S you can think of as a sum of these a set of these minor specifications, each of these S's, and sigma of S is going to be a product of the size of S minors that do involve A11 and 6 minus that number that don't. And these coefficients, so we'll talk more about what these sigmas are in the next slide. But for most of the rest of the talk, after we talk about a few other things, we're going to talk about what these coefficients are. So the coefficients are kind of the last remaining thing that we need to explain at this point. But I want to point out one really nice property that's completely unexpected and that we still don't have an explanation for, is that there's a symmetry in the coefficients. So if you look at B1, the integer coefficients that arise are -3, -1, and +1. And on the other end, B5, they have the same coefficients, -3, -1, +1. And B2 and B4 also have the same coefficients, 4, -3, and 1, 4, -3, and 1. So there's some you can figure out pretty quickly what the correspond, like why is it this one that has -3 and why does that one correspond to this one? That's, you just take some complements and that works out pretty easily. But why are the coefficients the same? That's a big mystery. Okay, so this is a very notation heavy slide. If you don't care exactly about what the details of this sigma of S thing is, you can zone out for the next minute or two and it won't really impact the rest of the talk that much. I'm going to start with the coefficients and then define what we need to write them out. So this is A11B6 in its full glory. What we're going to do is write each of these 6 minors using this notation. So this is delta of a row set and a column set. The definition is right here. What we're doing is, in addition to the rows and columns that are specified here, we're also going to include the first row and first column. So that's what these unions do. And then we take the determinant of that submatrix. So for example, this one, delta 2, 3, 2, 3, this is saying take rows 2 and 3 from the matrix in addition to the first row, columns 2 and 3 from the matrix in addition to the first column, and take the whole determinant of that. So that's the determinant of the whole matrix here. B0, we can write in a really parallel way. These are minors not involving the top left entry, A11. So we'll write these as gammas. So these gammas just take the rows and columns as specified, extract them from the matrix, and take the determinant. But then we have this A11 to the 6th extra factor. So what we're going to do is distribute an A11 to the 6th to each of these other factors. So that's why this A11 is here. And then we don't have to worry about A11 because there's exactly 6 factors here. So we get 6 copies of the A11. And now these look completely parallel, right? So all we've done is deltas here and gammas here, but the arguments are exactly the same. And then we're going to take this one step further. I want to think of each of these as a monomial in deltas and gammas. So this is M stands for monomial. This is the monomial specified by these 6 minors. And it's these 6 minors because each one of these gets assigned to a delta. In this one, none of them get assigned to delta. They all get assigned to gamma, so I'm not writing anything here. So this is the definition of M of S. All of the row columns, minor specifications that do appear in S, you feed those to a delta, and all the ones that don't appear in S, you feed them to a gamma. So that's B6 and B0. Let's look at one of these intermediate coefficients that we want to write as a linear combination of products involving 1 delta and 5 gammas, right? That was the guess. So here it is in its full form, and here are the 6 possible minors that don't involve the top left entry. So each one of these M's is a product of 6 terms, one of which is a delta identified by the row and column specification that's here, and the other 5 are gammas. And there's a unique way to do this. So you can solve for these coefficients, and here's what you get. And a really nice thing that pops out of this is that all 4 of these coefficients are the same. And this kind of reflects this symmetry that I was talking about earlier, where it doesn't matter what the row and column order is when you're scaling matrices, right? These minors can all be turned into each other, right? This is the extracting row 2, column 2. This is extracting row 3, column 2. You can turn those into each other with a row permutation. So to capture that even more directly, we're going to create an equivalence class of minors that can be turned into each other through row and column specifications, and that's where these sigmas are. So the sigma of S is the sum over all the monomials that should have that we're pretty confident should have the same coefficient. So it's the sum over all the minor specifications T that are equivalent to S. So these 4 all get wrapped up into this sum. This one, there's only 1 element in its equivalence class, and this one also only has 1 element in its equivalence class. So this is where we get where we get these formulas. So each of these is really a sum of possibly many monomials if there are more than 1 element in the equivalence class. So dropping back to the 2x2 matrix, Nathanson's formula was an explicit formula, but of course this is a degree 6 polynomial. So, we know that there aren't generally going to be explicit formulas and radicals for solutions of degree 6 polynomials. So this is the best we can do. So maybe we should also recast Nathanson's formula for 2x2 matrices, not as an explicit formula, but as a polynomial instead. And so this is what you get. And indeed, this can be written in the same way using these sums over equivalence classes of monomials involving minors that either involve the top left entry or don't. So this suggests that actually we have a pretty good idea about what these polynomial equations are going to look like for n by n matrices in general. In particular, the degree should be, why was the degree 6 here? It's because there were 6 minors that don't involve the top left entry. More precisely, the 6 minors that don't involve the first row or first column is the more correct way to say that. And for 2x2 matrices, how many minors are there that don't involve the first row or first column? There's 2. There's the 1x1 minor here, and there's the empty minor. And so you can actually count very explicitly the number of minors that don't involve the first row or first column in an n by n matrix, right? You have j choices. If you're looking for a j by j minor, you have j choices for the row and j choices for the columns. And it works out to be this central binomial coefficient. So for 2x2 matrices, we get degree 2. For 3x3 matrices, we get degree 6. For 4x4 matrices, we should expect degree 20 equations. For 5x5, we should expect degree 70. For 6x6, we should expect degree 252. All right, so for the remainder of the talk, let me back up. We're going to ask about these integer coefficients. So what are these integer coefficients? We think, as far as except for the integer coefficients, we're pretty sure what these polynomials look like. They look like, sums of the appropriate sigmas, and these are the degrees. So the last remaining piece is to figure out what are the integers in front of them. So we tried to run the Grosvenor basis computation for 4x4 matrices, and we let it run for a week or two, and it didn't finish, and so we gave up on that. So the Grosvenor basis computation doesn't seem to be feasible for 4x4 matrices or larger. So instead, we went back to PSLQ and tried to interpolate the full polynomial. This is a degree 20 polynomial for 4x4 matrices from numeric examples instead. Right, so you take a 4x4 matrix with integer entries, you scale it, you look at the top left, iteratively scale it till you get a fixed point, look at the top left entry, use PSLQ to try to identify what polynomial it satisfies, and then you do that for a bunch of matrices, and then you can start interpolating each coefficient as a function of the matrix entries. And this worked for 4. So we were able to get an explicit polynomial for 4x4 matrices this way. For degree 5, the computations, the systems of we needed what was exactly? I think that we needed too many. The systems just got these are linear systems now because you're trying to interpolate. You're just trying to find coefficients. But the systems got really large. And for 6x6 polynomials, we couldn't get PSLQ to finish with high enough precision. The numbers were just too large, too high precision. So to get more data to try to figure out a formula for these integer coefficients in general, we generalized to rectangular matrices. So an m by n matrix with positive entries, we define its Sinkhorn limit to be the matrix obtained by iteratively scaling so that the rows have sum 1 and the column sums are m over n. So in the case of when you have a square matrix, m equals n, and this gives you back your old definition. But the thing is, you can't have a doubly stochastic matrix that's not square, because the sum of all the row sums is the sum of all the entries, and the sum of all the column sums is also the sum of the entries, right? So you can't have the row sums all adding up to 1 and the columns all adding up to 1 if you don't have a square matrix. So this is a generalization. And the existence of this Sinkhorn limit was shown a few years later, not in this form, but in a more general form by Sinkhorn after his first paper. And this became a big software engineering project. So we spent a year and a half of CPU time scaling matrices and running PSLQ to recognize numbers just to get as much data as possible. Because degree 4x4 matrices, we're looking at degree 20 equations, and each coefficient has a sum of a bunch of sigma. So there was a lot of coefficients that we needed to solve for. So we ended up recognizing 100,000 algebraic numbers. This let us solve for 63,000 coefficients numerically, and then there were another 56,000 that were parameterized by free variables, which was annoying because if we could solve these linear systems exactly, it would have given us a lot more data. But the solutions were unique. But this is the conjecture. So I'm skipping a lot of steps, and we'll go back to some of them. But this is the final conjecture, and we don't have a proof of this. So there's a lot that we don't know. But here's the conjecture. For every m by n matrix A with positive entries, the top left entry x of the Sinkhorn limit satisfies this polynomial equation. So these things we've seen before. This is the monomial in the deltas and gammas. So it's just a product of minors of the original matrix. And the coefficient seems to be the determinant of basically an adjacency-like matrix. So this is where the combinatorics comes into play. There are some things I haven't defined here. This is what we're going to be focusing on next. So this is an adjacency-like matrix reflecting S. So remember, S is a set of minor specifications. M and N are the size of the matrix you're looking at. This is the set of all minor specifications for an m by n matrix that don't involve the first row or first column. So you pick a set of rows that don't involve the first row, you pick a set of columns that don't involve the first column, and you need to have the number of rows and the columns be the same because you need to square matrix to take the determinant. So this is what you're summing over. The size of this set is this binomial coefficient. So that's the degree of this equation because this goes up to x, x is being raised to the size of s power here. So this is the final goal. The other thing I'll say is that this adjacency matrix, so what we're gonna do is fix. We started by fixing the size of the matrix, right? But to get formulas for the integer coefficients, it's better to fix a coefficient you're looking at and change the size of the matrix, and then you can hope to get an actual formula for the coefficient. And when we do this, this seems to be an adjacency matrix with entries that are linear in M and N. So here's an example. Fix this to be your subset. So we're looking for coefficients of this monomial. So this is delta of empty empty, and times times all the other gammas. And the size of that product is going to change as you vary the size of the matrix, but there's some compatibility. There's a single relationship between all those coefficients. Let's try to fill in this table. So for 2x2 matrices, we're looking at the coefficient of m of empty empty or sigma of empty empty, and this is the equivalent version of Nathanson's formula for 2x2. So this coefficient is -2. For 3x3 matrices, this is going to be in the B1 coefficient because this set of minor specifications just has one minor specification in it. So we're looking right here. So its coefficient is -3. And since we have an explicit formula for 4x4 matrices, we can go extract the coefficient from there. And since we looked at a bunch of other matrices and have data for those as well, we can pull all the data together. And so this is what we started doing, like looking at a bunch of tables like this. This one is pretty easy to guess. It seems to be -n. And and at this point, we wouldn't have known that we didn't know that this was going to come from a determinant. But since I spoiled the answer by telling you it's going to come from a determinant, this is the determinant it comes from. It's a 1x1 matrix because again, this set has size 1, and there was a 1/m factor in the determinant. I don't know if you noticed, but this is really going to come from this. So let me remind you what an adjacency matrix is, in case you haven't seen it in a while, just for a graph, because I said we're looking for adjacency-like matrices, and the reason we know that is because of the way that adjacency matrices behave. So just for a graph, for a k vertex graph, the adjacency matrix is a k by k matrix with entries 0 or 1. The ones tell you which edges are connected to each other. So you get a 1 in the ij entry if vertices I and j are connected by an edge and a 0 otherwise. So for this graph here, this is its adjacency matrix. This one right here, this is in the first row and third column. So this is telling us that vertices 1 and 3 are connected by an edge. And adjacency matrices have this really nice property when you take their determinants. The determinant breaks up along connected components, right? Because the adjacency matrix is going to be a block diagonal matrix, right? Here we have two components in this graph. So we have a bunch of zeros here indicating that those two components are not connected to each other. And the determinant of a block diagonal matrix is the product of the determinants of the blocks. So this is what we were seeing. We were looking at a bunch of these formulas, and we saw that, okay, a lot of these formulas, these polynomial formulas factored in certain ways that suggested that into polynomials that we had seen earlier for smaller sets of minor specifications. And so this really suggested that, okay, there's some connected components going on. We just don't know what the structure is that we're looking at, right? We don't know what structure we're getting connected components from, but it strongly suggested that there was some kind of connected component structure underneath. So it turns out that the underlying graph is the vertex set S. So for the example on the previous slide, where we were just specifying one minor specification, the empty set of rows and the empty set of columns. That'll just be a graph on one vertex, so not very interesting. What are the edges in this graph that we're looking for? We started calling these links because when you start drawing minors on two-dimensional matrix diagrams, it made more sense to call them links rather than edges, but you can call them edges. So it turned out that there were two types of edges or links. This is type 1 links. And here now we're just looking at edges between two minor specifications. So you can imagine this is a 5 by 5 matrix. We don't care what the entries are because we're just interested in extracting minors. In the specifications of the minors we're extracting. We're not actually going to be extracting the minors. So here we have two minor specifications. This says row 2 and column 2. So that's this green 1 by 1 minor. This is rows 2 and 3 and columns 2 and 3. So that's this 2 by 2 minor. This first minor is a subset of the second, and their sizes differ by 1. So that's the first type of link. Here's another example. 2 by 2 minor inside of a 3 by 3 minor, and a 3 by 3 minor inside of a 4 by 4 minor. You get the idea. So this is what type 1 links look like. So these things, whenever you have a pair of minor specifications that have this relation, they're going to put a little link in a little edge in your graph that you're building that you're gonna eventually look at the connected components of. And the other type of link is when two minor specifications have the same size, but they differ in exactly one row or exactly one column. So here are two 1 by 1 minors that share the same row, but they differ in their column. Here are 2 by 2 minors that share the rows and differ in exactly one column. 3 by 3 minors that share their rows and differ in exactly one column. So these are the two types of links. We don't know, we have no idea why these are the right things to look at because this is all empirical, this is all conjectural. So if anybody has seen anything like this before, I'd be really interested to know after the talk, because it'd be nice to connect this to other things in the literature, and it may even suggest a whole proof of this conjecture. But these are what build up the connected components. So for example, this set of 4 minor specifications, how many connected components are there? Well, this green 1 by 1 is connected to this purple or this blue minor, 2 by 2 minor, but neither of those is connected to either of the other two. But the orange 2 by 2 is connected to the 3 by 3. So there's two connected components, the 1 by 1 and this 2 by 2, and then the orange 2 by 2 and the 3 by 3. But if we slide the orange one unit to the left, now suddenly it becomes connected to the purple 2 by 2 because now they share columns but differ in exactly one row. And so this one only has one connected component. So this adjacency matrix should be determined by these linked pairs. And of course, we have to figure out what happens on singletons also, because we need to know what happens on the diagonal of the matrix. And so here's what it is mostly. For every set of minor specifications, this adjacency matrix is going to be a k by k matrix, where k is the number of minors that you're looking at. The diagonal entry II is going to be the size of the ith minor specification times n plus n minus mn. If you remember back to the example we did, it was just minus mn because the empty set has size 0, so this term disappeared. And the off-diagonal entries capture these linking the two types of links. So unfortunately, this is the best way I found to write this, which is not a great way to write it. But you want to look at, you want to look at what's missing between each pair of row sets and what's missing from each pair of column sets. And you can write out the linking conditions by saying that, like, okay, if one is a subset of the other, then this is going to be empty. And if their sizes differ by 1, there's only going to be one element here. And so basically the entries are quite simple. These are the off-diagonal entries, mn, and 0 if there's no link. These first two cases are the type 1 links, where you have a subset that's one size smaller than the other one. And these are the type 2 links, where they have the same size, but they differ in exactly one row or exactly one column. But what are the signs? So I have them as plus or minuses here. We were stuck on this for a year and a half until last month. So we posted a paper on the archive. We basically gave up. So in September, we posted a paper on the archive saying, well, the matrix looks like this, and there's some sign assignment that always seems to work, but we don't know how to describe the signs in general. And so we did so here's an example. So we have this underlying graph that's built up by these two types of links. And the really annoying thing was that you can have the same exact graph underneath, but the signs are not the same. So that's telling us that the signs, whatever they are, they depend on some extra combinatorial information than just the underlying graph. So here are two 5 cycles. So these are 3 by 3 minors. This one, they all have the same row set. These column sets differ by 1 column. These also just differ in 1. These differ in 1. These differ in 1, and then these two differ in 1. So that's a 5 cycle as your graph. Here's the matrix that gives you the right determinants. So the determinant of this matrix agrees with values that we computed numerically. But this example, this set of minor specifications, is also a 5 cycle, and you need to perform a sign switch on one of the pairs of off-diagonal entries in order to get that determinant to agree with data we computed. And this is really close to the wire, because I think for one of these, we only had a single numerical coefficient to test it against. So it was like really, really close. This would have been completely impossible, before computers, unless you had some completely different way of approaching it. So what we did was we asked ChatGPT. So in February or late January, ChatGPT released their O3 model, which was supposed to be really good at doing research. And I had tried ChatGPT before with things, and it just completely, it lied to me, or it said something that was extremely promising, and then I realized that, okay, you don't know what you're talking about. And it said some self-contradictory things, but it got enough right that we were able to figure out something that works empirically. And so here's what you have to do. You have to, these are sets of columns indices, but you have to treat them as ordered. And so what you have to do is you have to look at them, put them in order, and then you have to ask, okay, what are we doing when we're going from 2, 3, 4 to 2, 3, 5? We're swapping out the column 4 and we're swapping in the column 5. But 4 and 5 are in the same place relative to the other columns. And so this, you have to think of this as a permutation where 4 and 5 are kind of playing the same role. So this permutation is the identity permutation, and it has sign 1, positive 1. This permutation, what are we doing? We're keeping 2 and 5, and we're replacing 3 with 7, but 3 is in a different place than 7. That's a single swap, so that's, the sign of that permutation is -1. And so this is what determines the signs. So the signs are positive, negative, positive, negative, negative, and then you can see that in the matrix here, positive, negative, positive, negative, negative. This set of minor specifications doesn't have the same signs. So going from here to here, 2, 3, 4 to 2, 3, 5, again, you're just swapping the 4 for 5, so that has a positive 1. The sign of that permutation is positive. But going from 2, 3, 5 to 3, 5, 6, we're getting rid of the 2 and introducing 6. That's 2 swaps to get the 2 to be at the end of the list. And so this has a positive, this picks up a positive sign rather than a negative sign. And so that's the signs, thanks to ChatGPT and parsing through ChatGPT's very long explanations. The thing is, ChatGPT, it never says, I don't know, right? Like, if you don't know, just tell me. But no, it won't tell you. It'll just try to convince you of something that's wrong. So it kept saying that the product along cycles has to be positive, which is not true, right? Like, this is a cycle, and the product along the cycle is negative. But what it means is, like, I don't know what it meant, but anyway, this was enough to, thinking about permuting the rows and columns was enough to figure out this missing piece of combinatorics that determines the signs. So here's just a summary of what we found. So each entry in an m by n Sinkhorn limit seems to be algebraic with degree at most this. This has a combinatorial interpretation. This is the number of minors of an m by n matrix that don't involve the first row or first column. The polynomial entry that describes one of these, algebraic numbers is a linear combination of things that look like this. So this is a product of minors. It's a monomial in the deltas and gammas. And the coefficient here is the determinant of an adjacency-like matrix. And all of this is conjectural. So with our theorem, we have one theorem, which is for 3 by 3. That's just computed by, that's just a computation that we were able to carry out. Everything else is conjectural. So there's lots more to do here. But I'll stop there. Thanks very much. Yeah.
Your links are bi-matroid. So
bi-matroid exchanges. Okay, great.
Might this explain the symmetry square?
That's a great question. I don't know. We maybe looked at that for 5 minutes, but we didn't. Yeah, I don't know anything about that. That's a good question. Yep.
That's the convenience if you try to plug that conjectural symmetry into the formula of the determinants you got.
Yeah, so we saw this. So the question was, we have this symmetry for the 3 by 3 polynomial and also for the 2 by 2 polynomial. I didn't mention that, but it's also right here, right? The 1 and the 1. And so, my hope was, okay, once we find a formula for these coefficients, we'll be able to see why they're symmetric, right? Like, how hard can it be? The problem is that for these coefficients, they're determinants of 5 by 5 matrices, and these coefficients are determinants of 1 by 1 matrices. So why are they giving the same determinant? There are certain results that tell you that, okay, a matrix of a certain size is going to have the same determinant as a matrix of a different size. I looked at this for a little bit, but I wasn't able to like find any standard result that explained the symmetry. Yeah, so that's a really good question. Yeah, Alejandro.
Also be written with this relation.
That's a really good question. I don't know. I want to say not really, because we're assuming. I'd have to think about it more. My temptation is to say no, because well, it certainly wouldn't be able to be written as in the sigma notation, because by looking at a symmetric matrix, ironically, you're destroying symmetry. You're destroying the symmetry. You're not allowed to permute rows and columns anymore. So the equivalence classes are no longer equivalence classes. Can you write them using the monomial, using the M's? Yeah, maybe. Yeah, I'd have to think about it. Yeah. Yeah, that's a great question. So if we start scaling the columns first instead of the rows, what happens? It turns out the limit is the same. So it doesn't matter. There's a characterization of the Sinkhorn limit. It's actually you can maybe see it mostly from this. So it turns out that there's a unique doubly stochastic matrix here that you can get from A by multiplying on the left and right by diagonal matrices. And moreover, the diagonal matrices are unique up to scaling. So, you could always like take a factor of 2 from R and put it in C. But other than that, the R and C and the Sinkhorn limit are unique. So yeah, it's pretty robust. You don't have to start with the rows. Yeah.
I was thinking, what if you start with the rows? What if you do one with the rows, one with the columns, and then average that for like one?
So you mean like take 2 copies of the matrix, scale the rows in one of them, scale the columns in the other one, and add it together? Great question. I have no idea. Yeah. Yeah, I don't know. Yeah.
So you have this in your formula, these powers of the A11.
Yeah.
You replace the X class, and can you start canceling these terms? Or
Yeah, so you could, if you replaced X by A11X, is that the right way to do it? Yeah, then it should remove this homogeneity power of A11. Yeah, so maybe that's the right thing to do instead of defining your gammas to have this A11. We swept the A11s under the rug here, but yeah, maybe that's a better way to do it. I don't know. Yeah, that's a good question. Yep.
I have 2 quick questions.
Sure. Yeah.
What strategies you change to get that massive speed up?
It wasn't that fancy. So I think there's Buchberger's algorithm, and what's the other standard Grosvenor basis algorithm? I don't remember what it's called. Huh? Yeah, I think that's more. I think that's more advanced and more recent. Anyway, Mathematica has two basic algorithms implemented. One of them is Buchberger's and the other one is the default one. So we switched to Buchberger's algorithm. And then we also, I don't know, there were a bunch of, it's in the paper actually. If you go to the archive, you can see exactly what settings we used. Yeah, it wasn't that, we don't really know what we're doing. Like I'm not an expert in Grosvenor bases. So basically I have Mathematica, which is this, interface to all these algorithms, and we just messed with the settings until we found one that worked. So yeah, that's yeah.
Is it like, I assume generosity or something, I expect I always have that degree?
I think so. So for the example, the 3x3 example that we started with, I mean, I guess, here's what I'll say. For all this, for all the data, except for the 3x3 case where we were actually able to compute the Grosvenor basis, all the other data was coming from PSLQ, recognizing a polynomial. So occasionally we would be recognizing an algebraic number that happened to have a minimal polynomial that was smaller than the expected degree. And so then, we were like having degree 20 polynomial, degree 20 polynomial, degree 20 polynomial, degree 8 polynomial, degree 20 polynomial, so we had to throw those out because we couldn't use them for interpolation. So yeah, most of that, we didn't have to throw many of them out. So yeah, it certainly can happen that for individual examples that the degree, this polynomial that we write might happen to factor. But yeah, generically, I think it is going to be this. Yeah. That's a really good question. Right, so this polynomial for the degree 6 example we started with, one of the 6 roots is this number, but what are the other 5? It wasn't obvious that that they have anything to do with the question. So in some sense, the polynomial, it's not, it's certainly a great answer, but it doesn't identify the root uniquely. So, is there some way to like say, okay, yeah, it's the root of this polynomial and actually it's this root. So it's not like there's a unique root between 0 and 1 that it has to be, or it's not like all the roots are positive. I mean, I think some of these polynomials have complex roots. So yeah, I have no idea what the other roots of the polynomial have, what information is there, if there is any. I don't know how. Yeah.
I mean, if you follow, like, for the first entry, there are like say 500 roots, right?
Yeah.
And then now if you then follow for every other entry, and if you apply.
You mean for the other entries in the maze? Yes. Yeah, exactly. Yeah, so right. Yeah, I don't know. That's interesting. Yeah. Yep.
Quite frequently, got some sort of dynamic system, you set up an equation saying, the fixed point that it converges, the fixed point that it converges to is the solution to some particular polynomial equation. It turns out what you really got to say is any stable point of the process is the root of this equation. And the equation also identifies not the convergence points, but also things like the divergence points. And particularly the Sinkhorn process known to have a divergence point that anything's known about.
I don't know. Yeah, the first place I would look is Adele's 100-page survey on the archive. So if it's anywhere, it's gonna be here. But yeah, I don't know the answer.
Well, let's thank Eric and Jan.
Thanks so much.